Hello everyone, this is section 12.10, the proof for Theorem 1, Lagrange's theorem. I've written the theorem right here for Bryce, who wasn't here. Miss you, Bryce. That we're going to let f and g have continuous first partials such that f has an extrema at the point x naught y naught on smooth constraint curve g xy equals c, g of xy equals c, if the gradient g of x naught y naught doesn't equal 0, then there exists a real number lambda such that the gradient f of x naught y naught is equal to the scalar multiple lambda times the gradient g of x naught y naught. All right, so let's begin the proof. Okay, we begin with the smooth curve g x y equals c, which we will represent as a vector valued function r of t equals x of t I hat plus y of t j hat, and that could be continued for more dimensions with the restriction that r prime of t does not equal 0. Where x prime of t plus y prime of t are continuous on open interval I. I'm going to switch pens. We're going to define, oh, that pen's not even better, okay. Define h of t to equal f of x of t, y of t. So because f of x naught y naught is an extreme value, and that's just part of the conditions in order to be able to use this theorem, then h of t, or h of t naught, is an extreme value of h. Since or furthermore, h prime of t naught, since h of t naught is an extreme value, the derivative of it would be equal to 0. By chain rule, since h of t is equal to, up here we defined it as this, h of t naught, we defined it earlier as this, so then it would be equal to f of x of t naught, y of t naught. We could write the derivative of that, and that would be fx of x naught y naught times x prime of t naught plus fy, or partial y, of x naught y naught times y prime of t naught. And this could be rewritten as gradient of f x naught y naught multiplied by r prime of t naught. And because it's an extreme value, we know that the derivative is going to be 0. So that is all equal to 0. So therefore, the gradient of f, or let me do a little therefore. Therefore, the gradient f of x naught y naught is orthogonal to r prime of t naught. And since gradient is normal to level curves, and this statement right here is a theorem that was introduced. It's Theorem 12.10 in the book. So if you want to go look more into that, you can look there in the book. I believe it's in section 12.6. So since gradient is normal to level curves, the gradient g of x naught y naught is also orthogonal to r prime of t naught. Okay, now since both of these gradients are orthogonal to r prime of t naught, then we could say, oh, Mr. Wells, hello, that consequently the gradients are parallel, so there must exist a scalar lambda such that the gradient f of x naught y naught is equal to that scalar times the gradient g of x naught y naught. Oh, word management. I apologize. There it is. We have done it.
Bye.